You're not going to have to stand up and say anything. I just need you to tell me what your hypothesis was, and then let's go over your data. Okay, so who volunteers? You guys are looking at your, okay, you've just volunteered willingly or unwillingly. Let me raise the screen and we'll write some of this stuff down. Okay. So what was your research hypothesis?
It was gray squirrels are more vigilant when it is cold outside.
They're more vigilant when what?
It's cold outside.
Okay. So gray squirrels are more vigilant when it is cold. Okay. So there we go. Now, how's about the numbers? What? So how many 5-minute segments did you have under each condition?
We had 5. We did a total of 10 for 3 days, so 30 total.
There are how many total?
30 total.
Okay.
We divided it up into 10 each day, and we did 3 days.
Okay, so you have 30 total. And over 6 days?
Just 3 days.
Over 3 days, so you did 10 a day,
Yeah.
right? So day 1, day 2, and day 3. Okay, so these days had different temperatures? Okay, so what was the temperature on the first day?
It was 58 degrees.
Pardon?
58.
Next
Then
day?
it was 79.
79?
Yeah. And then it was 82.
And 82 on the third day. Okay, so in each of these you had 10 observations. So what was, so in each 5-minute interval you're counting up how many times it was vigilant, right? So we're going to have 10 of those numbers for each day. So on day 1, how many was it? Okay, can you?
Yeah.
You've got time. We're going to do this twice because their design is a little bit different from what other people will have. So somebody else be ready. We're going to do 2 of these. Okay?
I'm 31 total. For the first day, there were 31 times that they were vigilant.
Okay, but I need not just 31. So let's look at your data sheet. So on this one, okay, under the vigilance column, you had 2. Okay, so I need 2. What's the next one?
0.
Okay,
12. 4. And 4.
okay, so that's 5.
Yeah.
2, 3, 4, 7, and 3.
Okay, so on the day 2, the 79 degree.
2, 4, 0, 0, 1.
2, 2, 1, 2, 2.
Okay, and on the third day?
1, 3, 2, 1, 4.
3.
3?
1, 1, 1,
Okay. So that's the way we're going to analyze these data is a little bit differently than the way other people are going to analyze their data. Because what this group is doing is they're looking for a pattern. So we're going to look at it like this. If this is temperature on this axis, all right, they're saying gray squirrels are going to be more vigilant when it's cold. So if it's cold here and warm here, pardon the graph, they're more vigilant when it's cold, and this is vigilance, then you expect the relationship to look like that. Okay? So the problem that we have is, how do we figure out what that line is? Okay? Well, fortunately, Excel does that for you. Okay? So they're predicting that the slope of this line is going to be negative. That's a line, and a line has the equation y equals mx plus b, where in this case, x is temperature and y is the amount of vigilance, m is the slope, and b is the y-intercept. The way Excel does this is as follows. Excel knows that the line is going to go through the point x bar, y bar. So that point is a solution to the line. Excel knows that. We can prove that by solving these equations called the normal equations. We're establishing a function. We're trying to find the minimum of that function, right? We do that by taking the partial derivatives of the normal equations and then finding the minima of those two equations. We solve it and we discover that that is a solution to the line. The next thing we know is that the slope of that line, okay, that's equal to the covariance of x and y divided by the variance of x. Okay? That's also a result of the normal equations. That's the least squares solution. Okay? So that's what we're going to do in Excel. And let's do that. I'm going to cover up your numbers, so you're going to have to read me your numbers again. I'm sorry. I'm assuming that everybody here has some familiarity with Excel, is that right? Okay, if not, now is an excellent time to do that. So we have three groups here, right? We have, what was the first temperature, 58?
Yeah.
Okay, and the next temperature was?
79.
79. And the next temperature was?
82.
82. Okay, so now I want you to give me the same numbers for the 58-degree temperature.
All right. 2, 0.
0.
Yes, 0. 12. 4. 4.
2, 3, 4, 7, 3.
Okay. And then for the 79-degree.
2, 4, 0, 0, 1.
2, 2, 1, 2, 2.
Okay, and then for the 82 degree,
Oh, sorry.
go ahead.
1, 3, 2, 1, 4.
3, 1, 1, 1, 4.
Okay, so now, because of the way Excel works, I'm going to have to reorganize these data. And what I'm going to do is I'm going to move all of these guys over one column, like that. And I'm going to put this 58 right there, and I'm going to copy that 58. I'm going to take these numbers and I'm going to drop them down. And I'm going to take my 79 and I'm going to copy it over there like that. And then I'm going to take these numbers, that. I'm going to take my 82, put it right there. Okay, so now on this axis, that is my x-axis, and here's my y-axis. Okay? So now what I want to do is, the first thing, I want to make a scatter diagram of these points. So I'm just going to go over here to insert. Can you guys see that? Let me make it bigger in a moment. And put in a scatter diagram. There we go. There's our scatter diagram, and it looks awful. Let's make it bigger. Okay, so the first thing let's do is let's change this x-axis. So format that axis. And the minimum value, we're going to make that 55. There we go. That looks much better. Okay, so now what I want to do is I want to add a trend line. So I'm going to right-click, add a trend line, and I want a line, and I want to display the equation on the chart and display the arc square. Okay, so now I'm going to hit enter, close that, there we go. And I'm going to move this stuff up there like that. Okay, so what was our prediction for the slope? As temperatures were colder, right, they were going to be more vigilant. Was that correct? Gray squirrel's more vigilant when it is cold. So here it's colder, right? So we predicted the slope would be negative, and in fact, the slope is negative. Okay? So this result is consistent with their research hypothesis. It explains, the R-squared is 0.19. It explains 19% of the variation in the data. So roughly 20% of the variability that's associated with vigilant is explained by temperature. The problem we have is this. We don't know whether this slope right here is significantly different from 0. Okay? So they've not performed a statistical test. All they've done is find out if the pattern seems to be there. So the next step is to actually perform a statistical test. Unfortunately, Excel will not do that for you. Well, let's see. Oh, isn't that awful? Let's see. We need to install another package in Excel. I'll be dipped. All right, here's our fallback position. Let's see if we have a program called PAST on this computer. Nope. The hell is that? That's pain. pass. E-A-S-T. Nope. All right, so let's do this. Let's go to the web. Let's go to Google. And there we are. And let's look for pass.exe. I'm looking for a website out of Finland. I'll read it. Okay. We'll just go here, see what that. There we go. There is a, I will put the link for the website on my webpage. It's available through the Biodiversity Institute at the University of Finland in Helsinki. It's a relatively easy to learn statistical software package. It's relatively user friendly. And it's free. Okay, there we are. Awesome. Okay, there is our data. Let's open up Excel, get that over here. What I'm going to do is I'm going to cut and paste all the Excel data directly pass. So let's put that here. There we go. And now okay. Awesome. So now there is the same regression we did before. Okay. And there we go. All right. So here's the statistical table that's associated with that regression. gives you the slope. It gives you standard error, the probability that the slope is significant. The p-value is 0.01. What does that mean? When it says the p-value is 0.01, what does that mean? All right. Remember back in the very beginning, we were talking about science as this process of conjecture and refutation, right? Every time you have to make a decision, there's a chance that you're making the wrong decision. So, we are able to affix a probability statement to that decision. And what we're saying is, unless we're really sure, we're going to reject that piece of information. And we have an acceptable error rate. And we're willing to be wrong 5% of the time. That means we're probably going to be right 95% of the time. So we use, as a cutoff, a p-value of 0.05. If the p-value is 0.05 or smaller, okay, then we say we have a significant relationship. All right? So in this case, the p-value is 0.01, which is smaller than 0.05. So what we're saying is the slope of this regression line is different from 0. It's not flat. We're 95% sure that it has a negative slope to it. Okay? So, the data that they have supports their hypothesis that the squirrels are going to be more vigilant when it's cold. Does that make sense? You guys follow that? All right. So, what they need to do now is the following. They need to say, okay, what was the null hypothesis? What was the alternate hypothesis? Their null hypothesis was probably there's no difference, okay, in vigilance with respect to temperature. So at cold temperatures versus hot temperatures, the amount of vigilance is going to be the same. What they've discovered is they've not accepted that null hypothesis, they've rejected the null hypothesis. They've accepted their alternate hypothesis. Their alternate hypothesis was that squirrels are going to be more vigilant when it's cold. These data support that alternate hypothesis, which is consistent with their research hypothesis. The next thing they have to do is explain why they think that. Okay? Why do they expect the squirrels to be more vigilant when it's cold? Okay? All right. So, why do you think they should be more vigilant when it's cold? What's the logic? You had a reason for coming up with that idea. What are some possible explanations? Okay, how hungry are the squirrels going to be when it's cold versus when it's warm? What's their energy budgets like? It's going to be hungrier because you're spending a lot of energy just on staying warm. Okay? So there you are. You've got to be out there and you're feeding more. But not only are the squirrels hungrier, who else is hungrier? The foxes and the hawks. Okay? So everybody that eats squirrels is hungrier too. So in other words, it's a more dangerous environment for the squirrel. The squirrel is forced to feed more because the temperatures are cold. And everybody else is on the lookout for something to eat as well. So it makes sense that you would expect these guys to be more vigilant when it's cold because it's a more dangerous environment when it's cold. Okay? All right. Most of you are not going to have a path to analysis that looks like that. Who else has some data what do you got? What was your hypothesis?
It was that squirrels are more vigilant when there's more people around.
Okay. So you have two scenarios, one where there are a lot of people and one where there are a few people? Okay. Those data are going to be analyzed a little bit differently, so let's look at those data. Okay, so you had two groups, one with few people and one with many people. Okay, so how many total observations do you have?
We did 30 total, 15 on each.
15 on each. So tell you what, let's just go ahead and put the numbers right into Excel, shall we? To save a little time.
So one of the things that kind of happened with our data there wasn't necessarily more people the next day. We went on a Friday, we went on a Saturday, but there were times when like people were walking through and there's more people closer by, and so I don't know if it's the days or maybe the difference.
Okay, so there are two things going on, right? I mean, you're making an assumption. Okay, that's fine. We'll deal with that. All right, so you have a Friday
Yeah.
and you have a Saturday?
Yep.
Okay, so what am I missing? There we go. Okay, so read me some numbers from Friday.
I have 10, 3, and 4, 4, 1, 4, 3, 6, 13, 7, 6, 2, 6, 11, and Holden has 1.
Yeah. So there's one.
The last one is one here?
Yeah.
Okay, and on Saturday?
Alright, so we're talking about vigilance, just to be clear, right?
Yeah.
Okay, yeah, so we had 4, 4, 4, 2, 3, 2, 0, 9, 2, 2, 3, 6, 3,
I have 3 and 6.
Okay. So, Now, to do this in Excel, the statistical test that we want to use is called a student's t-test. Okay? This is from a paper written by a guy who assumed the name student. It's kind of an interesting sort of story behind this statistical test. You have to remember that the whole idea of statistical testing is relatively new. Okay? In the time of the Romans, there's no way they would have ever had any of these ideas. The Romans didn't even understand the concept of probability. I think we've had that discussion, did we not? Did we talk about Jesus hanging on the cross and the people down, the Roman soldiers down below gambling or drawing straws to see who gets his clothing? You would have remembered that had we talked. You don't remember that? Great. So here's Jesus Christ hanging on the cross, being crucified, and these Roman soldiers are sitting around at the foot of the cross, drawing lots to see who gets his clothing. What were they thinking? Was this gambling? No. What were they thinking? Aside from the fact, gee, I hope I get the clothes. What were they thinking? They were thinking that it was God's will. So God was determining who gets the shortest straw or who gets the longest straw, and that's the person who gets the clothing. So God was choosing the soldier that's going to get the clothing. You recognize that it's strictly chance. They didn't recognize that. Why not? Because chance is a probability concept. And probability is the mathematics of the numbers between 0 and 1. The problem for the Romans is, well, what's the Roman numeral for 10? What's the Roman numeral for 5? What's the Roman numeral for 3? For 2? For 1? For 0? They didn't have a symbol for 0. In other words, the Romans had no concept of what nothing was. Without a concept of nothing, they have no way of understanding probabilities. They didn't understand chance. They didn't understand nothingness. You see that in the writing of the Bible as well. Because in the Bible, it's impossible. The whole thing is based on this conception that what was there before nothingness, right? They can't understand the concept that there was nothing before the present universe. There had to be something, namely a God. That's their view. They can't comprehend of nothingness. So now, as biologists, we're in sort of a similar boat. Pretty naive when it comes to understanding data and things of that sort. So there was the statistician who had a bunch of biologist friends, and the statistician is shocked and amazed that his biologist friends are such idiots when it comes to trying to analyze data. So he writes this paper, but he doesn't want to, on the one hand, he doesn't want to lose his friends. On the other hand, he wants to insult them a little bit. So he writes this paper, and he writes it under a pseudonym. And the name he uses as the author of this paper is Student. And the message is, any damn student could figure this shit out. Okay? So it's been called Student's T-Test, even though student isn't the name of the guy who developed the test. Okay? So it's so simple that even a student can figure it out. So what the Student's T-Test does is this. It's going to compare the mean for this group with the mean for that group. And it's going to come up with a probability statement. What's the probability that those two groups are the same? All right, so we've highlighted the group. Oh, criminy. Now we're back in the same spot where we need to figure out what the... All right, damn it. good with this version of Excel. Help. I want to insert, there is a new package, or there is a package available for Excel. God damn it. Where's the... analysis add-ins? Analysis tool pack. There we go. Data analysis, finally, thank you. Jeez, that's, okay. So now, so in other words, if you have a copy of Excel on your computer and it doesn't have the analysis tool pack in it, go to the help window, search for analysis, right, and then install the analysis tool pack. So we're going to scroll down here. All right, here are the t-tests. So paired two-sample for means. That's the one we want, okay? So t-test paired two-sample for means. There's also a t-test two-sample assuming equal variances. That's what we're going to use. We're going to assume that the variability in both groups is the same. I just click OK. All right, variable 1 range, I'm going to highlight the first column. Variable 2 range, I'm going to highlight the second column. And now I want output range. I'm going to put it right there and hit OK. And there are the results. So the average for Friday is 5.4. The average for Saturday is 3.5. So your hypothesis was what?
Vigilance is greater when there's more people around.
So were there more people on a Friday or a Saturday?
On Friday.
So at least in terms of the averages, it is slightly higher on the Friday than it is on the Saturday. But let's find out now if the difference is significant. So here's our p-value right here. It's 0.048. Our critical value is 0.05. So this is smaller than 0.05. So in other words, what do you do with your null hypothesis? Do you accept the null hypothesis or do you reject the null hypothesis? What does the null hypothesis say?
That there's little to no.
It says there is no difference between vigilance on a busy day and or when there are people versus when there are not people. In your case, there's no difference between vigilance on Friday and Saturday and or vigilance on
Friday or Saturday.
Yeah. Remember, the null hypothesis has to be completely opposite of the alternate hypothesis. The alternate hypothesis says that vigilance on Friday is going to be greater than vigilance on Saturday. That means the null hypothesis has to be there's either less vigilance or vigilance on Saturday is greater than vigilance on Friday. Okay? So you've discovered that that's not true. So the null hypothesis is rejected. You've accepted your alternate hypothesis that vigilance on the day when there's a lot of people is greater than vigilance on the day when there are few people. Okay? So the analysis is pretty straightforward. So what does it say about your research hypothesis? Your research hypothesis is something to the effect of vigilance increases when there are more people around. Does everybody follow that? Does anyone have a data structure which would not fit either this scenario or the previous scenario?
We did 2 different days to account for temperature difference at 2 different times. our research was based on foraging in the AM versus the PM. So we did a warm day and a cold day. If there's any difference based on temperature.
Okay. So let's look at
I
that.
only have half the data because my partner is quarantined.
Yep. So you have day 1, day 2, and then you have AM and PM.
Yeah.
And what was your research hypothesis?
That foraging will be greater in the AM.
Okay. So, and why is it on 2 different days?
We were the impression that we needed to do it on a warm day and on a cold day to account for the possibility that temperature would affect foraging.
Okay. So you have, which day was warm, which was cold?
Day 1 was warm, and day 2 was cold. Relatively speaking.
Okay. And how many observations do you have in each?
8 for each.
So you have 8 there. So there are a couple of ways to look at this. And you really just care about the AM versus the PM, right?
Yes.
So one possibility is to do 2 t-tests. One t-test comparing warm with cold, the other t-test comparing AM versus PM. But that presents a problem. What's the potential problem?
Can you compare those 2 different values?
What do you mean?
Like comparing the AM between day 1 and day 2, can you compare that between the AM and PM of day 1?
Yeah, so you're going to have all of these values and compare them with all of those values. So you're going to compare that with that. And then you're going to compare that with that. So you're doing 2 t-tests. What's the problem with doing that?
We get 2 different numbers, right?
Yeah, you'll get one. Perhaps this one turns out to be not significant, and perhaps that one turns out to be significant. I don't know. Maybe it's the other way. Maybe they're both significant. There's still a problem. This cold day and warm day, early, late, okay? Are those things independent? Does one tell you something about the other? Well, the morning is likely to be cool. The afternoon is likely to be warmer. So it's also cooler to warmer here. Okay? So it's possible that those 2 variables are not statistically independent. In other words, knowledge of one tells you something about the other one. Imagine I have a container, a hat, and in the hat are ping pong balls. And I tell you the ping pong balls are different colors. 100 ping pong balls in there. And I go up to the first student, and before the student can even pull out a ping pong ball, I say, what's the probability that the ping pong ball is red? They have no idea. I go to the next student, say, what's the probability that the ping pong ball is red? This student pulls one out and it's white. The next student pulls one out and goes, I don't know, pulls one out and it's red. I now go up to the third student. The third student now knows something. So far, 2 balls have been chosen. One is red, one is white. And I ask the student, what's the probability that the ball is red? And the student goes, 50%, and pulls out a white one. I go up to the next student. What's the probability that the ball is red? Aha, so far, 1 red, 2 whites. The probability of a red one is 33%. And with each student that I go to, each student has a little more information about the system and is going to get closer and closer and closer to the true value. Okay? That's the same thing that's happening here. The probabilities have changed as a result of the fact that there's some sort of interaction that's taking place between time and day. So, how to analyze those data? When you guys were, how many of you have had genetics? So, did you ever work with Punnett squares? Okay. And what did you do with the results from your Punnett square? You applied some sort of statistical test, did you not? What was the name of the statistical test? The chi-square test. Okay. So a chi-square test is observed minus expected quantity squared divided by expected. Okay. So this looks just like a Punnett square. So you're going to use a chi-square test on this contingency table. And that chi-square test will tell you if the AM is different from the PM, and if the Saturdays are different from, or if the day 1 is different from the day 2. Okay? Let's see if chi-square is available. All right. Let's see if chi-square is available in past. Contingency tables, there it is. Okay, so when you can, if you're going to do the chi-square, you can use the contingency table function in past to analyze your data. Okay? So when you guys have your data for your contingency table, come see me or talk to me after class or something, and we'll get you going. All right? It's easy to do, but it's just not going to be a t-test or the regression approach. All right, so now what do? You've analyzed your data. What to do now? In the age of COVID, how do we approach this? In a typical sort of semester, what we would ask you to do is write a paper describing all of this. We're not going to do that. Okay? Here's what I want you to do. I want you to put together a poster as though you were presenting this at some scientific meetings. When you go to scientific meetings, there are spoken presentations, that's where you get up on the stage, on the platform, and you give your talk from a PowerPoint presentation. There are also poster presentations. Right outside the door here are 2 posters, okay, that were given by graduate students at scientific meetings. Okay, one is on prairie dog vigilance, the other one is on feral hogs, I think. Okay? How do you make those posters? All sorts of different ways. You can get Adobe Illustrator, you can do all those programs. They're great, they're wonderful, they're fantastic, they're also very expensive. Or you can make it in PowerPoint. If you have Microsoft Office, and as a student at SEMO, you get Microsoft Office. Okay? If you don't have Microsoft Office on your computer, get it. It's free to you as a student. Okay? You can open up a slide, so create a new presentation, open up a slide, and you can make that slide any size you want. What we're going to do is we're going to keep it simple. You're going to make that slide 8.5 by 14. 8.5 by 14 inches. Obviously, these posters that are out here were like 3 feet by 5 feet or something like that. Okay? You're just going to make it 8.5 by 14 inches. And then what you're going to do is you're going to populate this slide with your information. So you need a title, and you need your names, and your institution. Okay? Then you need a summary. And in the summary, that's equivalent to an abstract. Just very briefly, what was your question? How did you address the question? What did you find? Okay? So those 3 things. What was your question? How did you address the question? What did you find? This study was designed to determine if gray squirrels are more vigilant when temperatures are low than when temperatures are high. We evaluated that hypothesis by doing this, that, and the other thing. Results of the statistical analysis revealed that, in fact, squirrels were more vigilant when temperatures were low. Okay? Something very simple. So there's your summary. Not a lot of words. Keep it simple. Why do you keep it simple? Because as these posters out here, both of those posters have too much information on them. That's common with what students do. They're trying to pack too much into those things. Keep it simple, because when you're at a scientific meeting, nobody wants to stand there and read your damn poster. They don't want to do it. They've been drinking all week long. They can hardly focus their eyes anymore. They're so hungover. They're standing there sucking on their coffee, and what they want to do is they want to look at the pretty pictures, look at the graph, and they want you to explain it to them. Okay? So very brief summary, and then what you're going to have after the summary is your methods. Have some key points, right? First we did this, then we did that, then we did the other thing. Okay? Then you're going to have a section over here called results, where you have your graphs. Something like that. Okay? You might have your hypotheses down here. HR, H0, H1, something like that. And then down here, you're going to have your conclusions. Maybe over here, you'll have a pretty picture of a squirrel feeding on a nut or something. Okay? Maybe I can't draw a squirrel, so I'll just draw a bunny. Okay? There's your pretty picture. And over here's your conclusions. Okay, what do you conclude? Why is it important? What does it signify? Okay, what's the takeaway message? That's what goes right there. Okay? We're all good on that? Make it pretty. A nice background, right? Use a nice font. Make it look attractive. When can we make those due? Let's see, how many more weeks do we have before we go into shutdown?
4, 3 or 4.
I think we have this week,
3.
this week, 2 more weeks, and then Monday and Tuesday of that final week before Thanksgiving, right? See, this is, what is today?
Wednesday.
Yeah.
The 28th.
That, I figured that out. Well, I wasn't sure when I walked into class, but I figured out that it was Wednesday at some point early on. Let's see, Tuesday is November 3rd, right? So next week, the following week, 3rd, 10th. So 3 more, so this week and then 3 more. Okay? Yeah, good. So you could get this done by the end of next week, right? Yeah, you could. You could get it done by the end of the day today. But by the end of next week, you could have this done. Awesome. Everyone good with that? Questions about your system in particular? Problems that you're having with your system?
So you want to do by next lab, our next lab?
Yeah. A week from today. All right. If you have questions, email me. If you're having problems figuring out the statistics, email me. We'll take care of it. Okay, what I want to do now is just get you ready for the next little behavior module that we're going to do. What we're going to do is study a kind of predation, and we'll use gray squirrels again. And that's why I had you collect those data on safflower seeds, sunflower seeds, black oil, and gray striped, and then the cracked corn. Because those are the food items that we're going to make available to our squirrels. So we're going to get to the point where, as using the same groups we have now, we're going to ask a question about foraging in these squirrels. Foraging is a form of predation. The difference is pretty straightforward. What a carnivore does is a carnivore, the coyote catches the rabbit, kills the rabbit. The squirrel catches the acorn and kills the acorn. Okay? The difference is when the coyote catches the rabbit, all reproduction for that rabbit is over. That's the end of the line. When the squirrel catches the acorn and kills that acorn, the oak tree that produced the acorn lives on and will continue to reproduce. So the difference is in the extent of the damage. The carnivore, it's complete annihilation. For the herbivore, like the cow eating grass, it reduces future reproduction, but it doesn't eliminate it. Okay? So there's this difference between being a carnivore and being a herbivore. In both cases, you're taking energy from one trophic level and transferring it to a different trophic level. Okay? So when we think about how to go out and forage, you can imagine that a predator is under intense selection pressure to both find and consume prey. It's important to make good foraging decisions. If you don't, right, if as a predator you don't make the appropriate foraging decisions, bad things happen. You don't end up having enough energy to reproduce. If you want to successfully reproduce, you have to take in enough energy to be able to make it happen. So how you get that energy is crucial. What we imagine, what we expect if natural selection works, is that when animals make those foraging decisions, they're doing it in a way that's going to maximize their inclusive fitness. So an animal should feed in a way that maximizes its inclusive fitness. Well, there are two ways to do that, okay? You can do it as an energy maximizer, or you can do it as a time minimizer. An energy maximizer is going to attempt to maximize the amount of energy it takes in any foraging bout. The time minimizer is going to forage in a way that minimizes the amount of time that it spends foraging. So if you think about it from a squirrel's point of view, which one is it? On the one hand, the squirrel should try and spend as little time foraging as it possibly can, because while you're out there foraging, you're exposing yourself to danger. At the same time, you can easily imagine that the squirrel should be trying to get in as many calories as it possibly can, so that it'll be fat to get itself through the winter, so that when springtime rolls around, tra-la, tra-la, it'll be ready for love. Okay? So an energy maximizer is going to get the maximum possible energy return under a given set of foraging conditions. Okay? A time minimizer gets the maximum energy return possible, but this time in the minimum amount of time. Okay? So they're both trying to maximize energy, but one of them is trying to do it in as little time as possible, and this one over here, the energy maximizer, is not trying to minimize time, but trying to get the most energy it can from any particular foraging bout. Let's compare polar bears and grizzly bears. Okay? What do grizzly bears eat? Has anyone ever encountered a grizzly? Oh, you've not lived until you've encountered a grizzly. They're big bears. They're not these little wussy black bears that we have running around in Missouri. Grizzly bears are badass. You encounter your first grizzly and you know it's there, and every hair on your body is standing on end. Okay? You realize how massive these guys are. And they're so unpredictable. A grizzly bear, one time you run into it and it just looks at you and totally ignores you. The next time you realize it's going to come after you. And there's no way you can outrun a grizzly. The other interesting thing about grizzly bears, if you look at their claws, each claw is about 5 inches long. they've got 10 of them on each paw, okay? If the grizzly decides it wants you, it gets you. And it'll just open you up like a can of sardines. I was in this visitor center once in the Tetons, and this Bubba comes in, and he's going to go out hiking, and he's got this long hunting knife on his belt, probably an 8-inch knife or something. And the ranger says, "What's that all about?" And he says, "Just in case I encounter the grizzly." The ranger laughs and says, "Yeah, right. The grizzly's got 10 of those, man. There's no way." Guys go out with handguns trying to protect themselves against grizzlies. You go out there with a, with a 38 or a 9mm, all you're going to do is piss off the grizzly bear. Go out there with a 45, that's just going to make him really mad. Shoot him as many times as you can. All you're going to do is piss him off, and he's still going to kill you. You want to take him down, man, you're going to need like an elephant gun to take that guy down. And the problem with a rifle is you can't get it up before he's already on top of you. Grizzlies are amazing. What do they eat? Aside from the occasional tourist. What do they eat, you think? Anything they want, right? In the spring, they're eating berries, fresh vegetation. When they're lucky, they'll get salmon or something like that. But mostly, they have a very varied diet. What do polar bears eat?
A lot of fat.
Pardon?
A lot of fat.
They eat fat. They eat seals. Seals and sea lions is what they eat. 70% of the diet of a polar bear is fat. In other words, the polar bear isn't going to mess around with no berries, no grass, no dead lemming or something like that. No, the polar bear is going to catch itself a seal. Okay? Fat. That's what they're consuming. So the polar bear is an energy maximizer. So there's this trade-off now when you go out foraging between having a very specialized sort of diet and having a very generalized diet. Specialized diets, the food items are high value, but might require a lot of search energy or search time, and might also require a lot of handling. That's what happens with the polar bear. A generalized diet, the food items are more abundant, but they're not necessarily of equal value. And that's the case with the grizzly bears. Each food item that the animal consumes contributes to the average energy input. The better diet is the one that's going to increase the average energy input. So the question is, should the animal be a specialist or a generalist? Should the animal broaden its diet, or should the animal narrow its diet? And here's how we're going to answer that question. Energy input per item is going to be E over H. Okay? So E is for energy. H we're going to define in a moment, but that's for now, okay? That's just our energy input per food item. So we're going to compare the caloric content of each item to the handling time, hence the H, right? H for handling. In some sense, H is a measure of the energy required to process that thing, how much time you have to spend handling it, okay? That's going to be how much time it takes you to catch it, subdue it, and consume it, okay? So what we want to do now is create a very simple little mathematical model that's going to allow us to predict whether an animal should be a specialist or a generalist. So let's define the amount of time the animal spends searching for prey as T sub S. So T is time, S is search. So this is the amount of time the animal spends searching. Let's imagine the animal encounters two different prey items, prey item 1 and prey item 2. The predator encounters those prey items at different rates. One prey item is more abundant than the other one. So the encounter rate is going to be lambda. So we have lambda 1 and lambda 2. So now we have search time, which is T sub s. We have handling time, which is H1 and H2. We have the encounter rate, which is lambda 1 and lambda 2. And each of those prey items is going to have a different caloric value. So that's going to be E1 and E2. Okay? So now we have a series of terms defined. The number of prey items 1 it's going to encounter, or it's going to be the time spent searching times the encounter rate of prey item 1. And for prey item 2, it's time spent searching times the encounter rate of prey item 2. So it should get n sub 1 items of prey type 1, n sub 2 items of prey type 2. The total energy returned then is simply going to be, well, it got n sub 1 items of prey type 1 times the energetic value of prey type 1 plus the same for prey type 2. So total energy is simply going to be that very simple little equation. The total time spent handling those prey items is going to be how many of N1 did it encounter times the handling time for each item. And the same for prey item 2. So that's our total handling time. So then, if we do some substitutions for N1 and N2, we get the total energy is T sub s, lambda 1 E1 plus T sub s, lambda 2 E2. We can simplify that by pulling T sub s out. So energetic energy that the animal gets is T sub s time spent searching times lambda 1 E1 plus lambda 2 E2. Total time spent handling is T sub h, the same sort of algebra. T sub h is total time spent searching times the quantity lambda 1 H1 plus lambda 2 H2. So total time spent searching and handling prey is T sub s plus T sub h, and using our little substitutions, we get this nice little equality down below. And now what we want to do is figure out the energetic return per unit time spent searching for and handling prey. And that becomes this equation, E over T. And remember, that's what we're trying to maximize. We want this animal to forage in a way that makes this ratio there as large as possible. So it's all of this algebra up to this point. And we can simplify that to this equation. Okay? So that's all pretty straightforward. Let's do an example. Let's imagine we have a forager that spends 100 seconds searching for prey. This stuff comes from an experiment on nuthatches. There was this guy doing this little experiment on nuthatches. He had nuthatches in little cages and a conveyor belt going through each cage. And in the conveyor belt was a little food dish. And in the food dish were little seeds and whatnot mixed up in sand. And the seeds were in different concentrations and all of that. There were different kinds of seeds. Different seeds required different handling time, different caloric values, all that sort of stuff. But that's where this whole analysis comes from. But let's imagine this animal has 100 seconds. The encounter rate for prey item 1 is 0.1, and for prey item 2, it's 0.01. So prey item 1 is encountered 10 times more often than prey item 2. Then let's imagine that the caloric value of prey item 1 is 10, and the caloric value of prey item 2 is also 10. Handling time for prey item 1 is 5, handling time of prey item 2 is 10. And the question is, should our predator be a generalist or a specialist? Let's figure it out. So let's write down our equation. We have E over T equals lambda 1 E1 plus lambda 2 E2 divided by 1 plus lambda 1 H1 plus lambda 2 H2. All right, let's figure out what the animal does, what it gets in its energetic return if it takes both food items. So lambda 1 is 0.1, lambda 2 equals 0.01. I think E1 was, and E2 are both 10. And then H1 was 5. And H2 was equal to 10. So what do we get if both food items are taken? Then we get lambda 1, which is 0.1, times E1, which is 10, plus lambda 2, 0.01, times E2, which is 10, divided by 1 plus lambda 1, which is 0.1, times H1, which is 5, plus lambda 2, 0.01, times H10, which is 10. H2, which is 10. So that equals 0.1 times 10 is 1, plus 0.01 times 10 is 0.1, so that's 1.1 divided by 1 plus the quantity. 0.1 times 5 is 0.5 plus 0.1, right? So that's 0.6, 1.6. So what is 1.1 divided by 1.6? Somebody get out your phone calculator, figure it out for me. What do we get?
.6875.
0.6875. Okay, let's repeat this now. Let's imagine the animal only takes food item 1 and doesn't take food item 2. Now what do we get? We get the same thing here, except that we're not going to worry about that. And we're not going to worry about that. So now that equals 0.1 times 10 is 1, divided by 1 plus 0.5, so equals 1 divided by 1.5, which is what? 2/3, right? So 0.67. Now let's imagine the animal takes only food item 2. Now we're going to get 0.01 times 10, which is 0.1, divided by 1 plus 0.01 times 10, 0.1, so it's 0.1 divided by 1.1. What is that?
Zero.
0.09, that's all we need. So what should the animal do? Should the animal be a generalist, or should the animal be a specialist?
The generalist?
Which one has the highest caloric value? This one. So the animal, if it's maximizing energy per unit time, should be taking both food items under these conditions. Okay? If it takes only food item 1, it has slightly lower return. If it takes only food item 2, it has considerably less return. So it should be taking both food items. It should be a generalist, not a specialist. See how I did that analysis? Easy. It's just simple algebra. Now, let's look at it from a slightly different perspective. Let's think about it from the perspective of an animal that has to go to its foraging patch. This is the point where it starts to travel to its foraging patch. From here to here is its travel time. From here to there is its patch occupancy time. So this is the amount of time it spends in the patch. This axis right here is energetic return. So you get into the patch and you start feeding, and at first the rate of return is really high. But then the rate of return starts to taper off because you've been pulling stuff out of the system. A little bit. You go fishing. Go to this nice little pond. You first show up and you're pulling fish out left and right. But of course, with every fish you pull out, there are fewer fish left. And it's harder and harder and harder to catch the remaining fish. The rate of return starts to taper off. The question is, at what point do you leave the patch to go to it? At what point does it no longer make economic sense to stay in that patch? The way we find that is by drawing the tangent line to that curve. That's where we leave. There's still energy left in that patch. If you stuck around, you could still get some more energy. Okay? But you're losing out if you do that. You'd be better off going to a different patch and getting back into this mode where the rate of return is high. Think about it in terms of how much time it takes you to get to the patch and what your rate of return is. If the travel time to the patch is short, the travel time starts off there, the tangent line goes up there, and you should leave the patch at that point. If the travel time is short, patch occupancy time should be shorter too. It's also a function of what the rate of return is. If the rate of return is really shallower, should you stay longer or should you stay shorter? Think about it like this. Let's imagine it's Friday night, we don't have COVID, you're going to go to a party. You're a guy, you're going to the party to meet some girls. So you go to the party's right next door. Okay? You walk in, you realize it's 15 guys and 1 girl. And you walk in, and your first thought is, bummer. Stick around, have 1 beer, say, gotta go guys, and you're gone. Okay? Now imagine the party's in St. Louis. You drive all the way up to St. Louis, walk in the front door, 15 guys, and 1 girl. Now what do? When the party was right next door, you have one beer and you leave. But now you've driven 2 hours to get there. Damn, one beer, maybe somebody will show up, another beer. Hey, what's that on the stereo? Another beer. Hey, did you hear about Billy Bob? Before you know it, you put away a couple of six-packs, okay? In other words, the travel time was longer, so the patch occupancy time ends up being longer too, all right? That's the way we want to think about foraging. We want to think in terms of what the payoff is to the animal. We want to think in terms of this marginal value theorem. When should it leave? How long should it stay? Right? And we want to think in terms of what's it getting out of this? Okay? Is it making the right foraging decisions? What I can tell you is that squirrels are insanely good at foraging optimally. You see those guys out there, they're burying those nuts, okay? And you're thinking to yourself, there's no way this guy's going to find that nut again. But if he's alive, he will find it, okay? If he dies, somebody kills him, he won't find it. The oak tree is depending on him getting killed. Because what the squirrel just did was plant the oak tree, right? Planted the acorn to grow a new oak tree. If the squirrel dies, a new oak tree comes up. If the squirrel doesn't die and eats it, no new oak tree. That's why the oak tree is producing such enormous hordes of acorns, an effort that at least some of them are going to make it. Okay, so here's what we have going on then. We know what the caloric value of 4 food items are. We have safflower, black oil, sunflower seeds, we have gray striped sunflower seeds, and we have whole kernel corn. Okay? And we know percent protein, we know percent carbohydrates, and we know percent fat. It turns out that black oil sunflower seeds are high in fat. Why is being high in fat a good thing for a squirrel?
The extra insulation for the land.
And forget about why is fat good?
More energy.
Energy. 9 calories per gram compared to 4.5 calories per gram. So protein and carbohydrates have half the caloric value of fat. So why are poor people generally obese?
Because crappy food's cheap.
Because crappy food is cheap and it tastes good, okay? And crappy food is high in fat. So they're getting a lot more calories with each meal than somebody who's buying more expensive food. Okay? Turns out that black oil sunflower seeds are high in fat, which is good for the squirrel because it gets a lot of caloric return on what it's taking. Gray striped sunflower seeds, not quite as much fat. These things also differ in terms of protein. Corn has very little protein, is mostly carbohydrates, and has very little fat. Okay? So the animal has choices in what it's going to feed. There are also differences in handling time. Safflower seeds, just pump them in your mouth. Black oil and gray striped sunflower seeds, you've got to work a little bit to open them up. Black oil are harder to open up than gray striped. Corn, you just start chewing on it, but it's hard, okay? So the handling time of these things differs, and the caloric value differs. And here's the fun thing that we can do. We can change the encounter rate for these food items. How can we change the encounter rate? We can set up food dishes for these animals, and we can fill that food dish with a known quantity of sand. And then we can mix in a known quantity of our food items. Okay? So we might have 1 liter of sand plus 50 grams of one of these food items, 1 liter plus 100 grams, 1 liter of sand, and 200 grams, 1 liter of sand, and 400 grams, something like that. We can change the concentrations of the food items. So you've got 400 seeds, or 400 grams of seeds in a liter of sand. A lot of seeds in there. Squirrel comes along, starts digging in that food dish, it's going to find them. You've only got 50 grams of seed, man, it's working through, oh, there's one. Yeah, oh, man, hey, there's one. But the encounter rate is lower. And he's worried about vigilance and being preyed upon. Okay? So we can change the encounter rate. We can put these food dishes in safe places, right at the base of a tree, or we can put the food dishes way the hell out in the open where the animal is exposed. And what we can look at, the metric that we can use, is something called the GUD, the giving up density. We're going to ask the question, what is the giving up density for this food item? Is the giving up density is what density of food items, at what density of food items does the animal say, enough, it's not worth it being in this patch anymore? Think of the marginal value theorem of that curve. At what point should I forget this patch and go away? That's the giving up density. So what we want to do now is use this idea of giving up density to try and explore foraging in our gray squirrels. Do our squirrels forage optimally? Are they behaving the way we expect them to behave? So over the next week, right, I want you and your partner to communicate with each other and develop some ideas about what your expectations are. These different food items have different values. You can compare a high-quality food item with a low-quality food item. Are the giving up densities the same? You might compare something that has a high handling time with a low handling time. You might concentrate on fat or on protein or whatever it is. You might concentrate on a safe place to forage versus a dangerous place to forage. Okay? But I'd like you, by next week, to have some basic ideas so that when we meet next week, we can formalize your hypotheses, we can get your designs set up, and we can even start getting all of your materials together so that we can do this. What I'd like to be able to do is run these experiments over a weekend or something like that so that when we come back before shutdown, we can collect our data and analyze our data. If we mix these seeds in with sand, okay, put a known quantity of sunflower seeds in the sand, we have these special sifting devices that we can use. We can sift out all the sand and actually measure how many seeds we have left. We can figure out how many they took, how many are left, right? We will know what the giving up density is. Okay? So that's on tap for next week. So with your partner, communicate with your partner, get some ideas going, be ready to discuss those ideas when we meet again next week. Okay? I'd like to get these experiments designed next week so that perhaps, you know, we can, by the end of that next week, you can pick up all your supplies and everything, and you'll be ready to get your experiment in place and up and running. Okay?